Hi everyone, my name is Tristan Bester from the School of Computer Science and Applied Mathematics at the University of the Witwatersrand, specifically the Robotics, Autonomous Intelligence and Learning Lab. Today I'll be presenting our paper, Counting Reward Automata, Sample-Efficient Reinforcement Learning through the Exploitation of Reward Function Structure. We will begin the presentation with a brief motivation of the research before introducing a running example, which will be used throughout the presentation. Reinforcement learning has seen a number of impressive applications in previous years, from video games to robotics. However, these applications have largely been constrained to relatively simple short-horizon tasks. This is a consequence of techniques used for reasoning and learning, where approaches have been constrained to strategies that rely on end-to-end learning systems. Previously, approaches have been proposed as solutions to these problems, including HRL and state machine-based approaches, each of which have limitations. We extend the current state-of-the-art state machine-based approaches with the introduction of a novel abstract machine. As a running example, we'll consider a task specification in the letter N environment. This environment is a simple grid world in which symbols are associated with positions. A symbol can either be observed a given number of times before being replaced by another symbol, or infinitely often. The agent is able to move in any of the four cardinal directions, and the dynamics are deterministic. At each point in time, an agent is able to observe its current position, as well as any associated symbols. For this example, we use a simple environmental configuration. The agent is able to observe the symbol A n times before it is replaced with the symbol B. We define a task in which the agent is required to observe a sequence of environmental symbols corresponding to a string in the given context-free formal language. We now show a trajectory in which the agent completes the task. The agent begins by observing the symbol A twice. At this point, the symbol associated with the position changes to a B, and this is observed by the agent. Finally, the agent observes the symbol C twice to complete the task. We now discuss how the reward machine formulation can be used to solve this problem. Reward machines are automata which can be used to model reward functions. The main benefit of this approach is that the structure of these automata can be used to increase sample efficiency. Notably, the policies learned by reward machines are optimal. Reward machines are finite state machines which have been augmented with an output function. The machine is given as input the high-level events taking place in the environment, and it returns a reward. As a result, two components are associated with each edge in the illustration. The first element specifies which high-level events are required for the transition, and the second element is the reward. We now consider how to design a reward machine for the example problem. Here we show an example reward machine for the case where n is equal to 2. We can see that the automaton is required to maintain a single state for each position of the agent in the target string. For example, the second state symbolizes that the agent has observed a single symbol A. This illustrates that different reward machines are required for different values of n. This is a consequence of the fact that reward machines are finite state machines, and finite state machines cannot model context-free languages. In summary, reward machines are finite state machines, and finite state machines are only able to recognize regular languages. However, this task specification requires a context-free language specification, and as a result, it can only be solved using more powerful automata. We present the counting reward automata formulation as a solution to this problem. We replace the finite state machine at the core of the reward machine formulation with a count machine. This is an automaton variant which has equivalent recognition power to a Turing machine. This allows us to model the reward in a similar manner to reward machines, while extending the set of expressible problems to all formal languages, as opposed to just regular languages. Here we show the counting reward automaton used to model the reward for the running example. More details about how the machine operates can be found in the paper. Here we specifically focus on the following important property. The machine is able to model all strings in a context-free language using a finite number of states. As a result, a single automaton can be used to model all task specifications in the formal language. We now provide an overview of the results. Firstly, we observe significantly improved sample efficiency. As a single automaton can be used to model all strings in the formal language, a single policy for the problem can be learned. This is not true for other formulations. Secondly, the state machines produced by our approach are significantly simpler. Here we show the number of states and edges required to solve a task as a function of its complexity. Notably, one counting reward automaton is able to solve all of the tasks in the specification. Finally, our framework integrates naturally with LLMs for task specification. The reward model for this task was specified using an LLM and solved using deep Q-learning. Please see the full paper for more detailed explanation of our approach. Thank you very much for listening.